So dear student, now we are entering into the next part of this chapter, that is 6C. Here we are going to take up finally the lenses and combination of lenses. But before that, we have one more stage that we will be discussing, and this is a refraction at spherical surfaces. So these four parts, 6C1, 6C2, 6C3 and 6C4, these four parts are something which you have never studied in optics in prior classes. It is an intermediate stage, you can say, between the basic laws of refraction and then the lenses. So before I come to the lenses, we will be discussing these spherical refracting surfaces. So if we talk about the spherical refracting surfaces, spherical refracting surfaces, we can think of two kinds of refracting surface, spherical refracting surface. One is a spherical refracting surface which is convex in shape. So a spherical refracting surface like this, I call it a convex spherical refracting surface. Why do we call it a convex refracting surface? Because its denser medium is convex towards the rare medium. So its denser medium is convex towards the rare medium. We call it convex refracting surface. Here, the refractive index of the air may be, or the rare medium can be represented by mu1, and refractive index of the glass can be represented by mu2, or denser medium. Now here we have certain points to discuss, like what this point will be called as. So this point, which is the center, this is the principal axis. So this point, which is the center point on the principal axis, and this convex refracting surface will be called as pole. So, and this line is called as what? Principal axis. And then we have a point called center of curvature. So if we imagine that this hole is part of a sphere, then obviously the center of that sphere will be the center of curvature. And this distance of the pole from the center of curvature will be obviously radius of curvature. So just we again leave this so that you don't get confused. So here we have a point called pole, we have a point called center of curvature. It is actually the center of that sphere of which this curvature is a part. And this line is principal axis, and this distance of center of curvature from the pole is radius of curvature. And you know, all the time, any line which you draw from center of curvature onto the surface, it is going to be normal, and it is going to have a value equal to radius of curvature. And then we have a term called aperture. So this distance, this shortest distance between the two edges PQ, the shortest vertical length between the two edges of this convex refracting surface will be called as aperture, PQ. So once again, the different terms we talked about. First, that this is a convex refracting surface because its denser medium has a convex surface towards the rare medium. Second, this line which passes through its center will be called as principal axis. This point will be called as pole. For this sphere of which this convex refracting surface is a part, you have a center of curvature. The distance of center of curvature from the pole is obviously the radius of curvature. And then this term called aperture, it is the shortest distance between the two edges of that convex refracting surface P2 and aperture PQ. So this is one side. We have seen the convex refracting surface. Similarly, we can also talk about concave refracting surface. So let's draw a concave refracting surface here. A concave refracting surface will, other terms will be the same. Just the difference is that this time the denser medium this time will be concave towards the rare medium. So denser medium has a concave shape towards the rare medium, and then once again this line which passes through it will be called as principal axis, otherwise everything is same. We call it principal axis. This point will be called as pole, and then if you just complete the sphere of which this concave surface curvature is a part, that sphere will have a center. It will be called a center of curvature. The distance between center of curvature and the pole will be called as radius of curvature, and any line which is drawn from the center of curvature onto this will be obviously normal and equal to radius of curvature. And then if we are looking for aperture here, so if I call it P, or if I call it M, if I call it N, so the shortest distance between the two edges of the concave mirror, the shortest distance between the two edges will be aperture. So that's how the basic terms in a spherical refracting surface. And from here, now we can talk a little bit more about what kind of formula for spherical refracting surface we are going to write. So let's see the formula for the spherical refracting surfaces and the many cases that we are going to see. The first case is that just imagine that you have a spherical refracting surface and then the object is in rare medium and its image is finally formed in the denser medium. So it's a case of rare to denser. I'll say it's a case of rare to denser. In fact, it does not matter that the image is going to be real or virtual. It may be a real image, it can be a virtual image also. For all cases of rare to denser, there will be same formula, and that formula is minus mu1. Mu1 is the refractive index of rare medium over u plus mu2, that is the refractive index of denser medium, over v is equal to mu2 minus mu1 by r. You know what is r? R is the radius of curvature of this convex surface. So for all cases of rare to denser, again I am writing, this is for very important, for all cases of rare to denser. When we say for all cases of rare to denser, it means it may be a real image, it can be a virtual image, it can be a convex or a concave refracting surface. For all cases of rare to denser, the formula for the spherical refracting surface will be minus mu1 over u plus mu2 by v is equal to mu2 minus mu1 by r. तो आप कई थोड़ा कंफ्यूज हो सकते हैं कि ऐसा कैसे कि रियल इमेज, वर्चुअल इमेज or convex refracting surface या concave refracting surface, in all cases, for all cases of rare to denser, the formula is same that we are going to prove. Second, आपने magnification का formula भी पढ़ा होगा. In mirrors you have done, the formula for magnification was I by O is equal to V by U. This formula of magnification we have done in mirrors, but this time will, because it's a two different medium case, so here it will be mu1 over V. जैसे minus mu1 over U था, so it will be mu1 over V over mu2 over U. We are going to prove this formula. So formula for magnification will be mu I by O is equal to mu1 V by mu2 U. So I am making you first aware of the relation, and then we are going to prove this relation in spherical convex refracting surface or concave refracting surface. For all cases of rare to denser, same formula. And now let's take a situation which is reversed. So if we talk about a situation which is reversed, it means think of for all cases of denser to rare medium. So this time we'll talk about that as though this light beam is now traveling from denser medium to rare medium. The object is lying in the denser medium and the beam goes and is finally making an image in the rare medium. So this denser medium will have a refractive index mu2 and this will have a refractive index mu1. In this case, in all cases of denser to rare medium, the mu1 and mu2 will exchange. If earlier it was minus mu1 over u plus mu2 by v, so I'll just write this case it will be minus mu2 by u. तो इस बार क्योंकि ये mu2 मीडियम से mu1 मीडियम में जा रही है, तो minus mu2 by u plus mu1 by v is equal to mu1 minus mu2 by r. तो आपने देखा there is a exchange of mu1 and mu2 now. For rare to denser, it was minus mu1 over u plus mu2 by v is equal to mu2 minus mu1 by r. And for denser to rare, it is minus mu2 by u plus mu1 by v is equal to mu1 minus mu2 by r. So that's how you can see for denser to rare, magnification भी उसी तरह से change हो जाएगा. Magnification is I by O is equal to V by U. But this time, this is mu1 V by mu2 U. It should change. If earlier the magnification was I by O is equal to mu1 V, mu1 to mu2. This time it will be mu2 to mu1. So it will be mu2 V by mu1 U, like this. So that's how you can see the case of rare to denser and denser to rare. And again, this case of denser to rare is for all. For all mean real image, virtual image, convex refracting surface, or a concave refracting surface. In all cases of denser to rare, the formula will remain same. Minus mu2 by u plus mu1 by v is equal to mu1 minus mu2 by r. In fact, this is the importance of a formula. We can't keep on recalling the formula for different situations, for real image, for virtual image, for convex surface, for concave surface. There should be one formula for all cases, like laws of reflection are same irrespective of any situation. Laws of refraction are same irrespective of any situation. Similarly, we should have a fixed formula for rare to denser and fixed formula for denser to rare for any kind of image, real image, virtual image, convex surface or concave surface. And that's what we have. It is actually something which is good to use and it is more comfortable as principle. So let's prove now these both cases. So let us now first find the expression and prove it for spherical refracting surface, that is air to denser. So first case is rare to denser, and we take a convex surface, convex refracting surface, and that too with a real image. We can also go with a virtual image. So assume you have a convex refracting surface this time, and here is going to be the principal axis. This point is pole P, and here is center of curvature C. And let there be an object here in rare medium. So from this object O, a beam of light is incident onto this convex refracting surface. I want to know where will it go afterward. So we draw a normal from center of curvature. Any line which is from center of curvature is normal, and this is going to be an angle I, angle of incidence. Now this beam otherwise would have gone here, but it will bend towards normal, and thus it forms an image, say at I. And if we look at this angle between the refracted ray and normal, it will be angle R. Let's name other angles also. This is alpha, and the angle made by image at the principal axis is called as beta, and angle by the center of curvature and normal, it is say gamma. So we can see there are 5 terms here: I, R, alpha, beta and gamma. First I want to have a relationship how I and R are related to alpha, beta and gamma. So my first point is how I and R related to in terms of alpha, beta and gamma. So can I say I as the exterior angle of, so can I say I is the exterior angle of this triangle including alpha plus gamma? So can we say I as alpha, I is the exterior angle of this triangle. So I being the exterior angle can be said as alpha plus gamma, equation number 1. And similarly, there is another triangle where we want to relate with R. So R, gamma and beta, among this triangle, gamma is the exterior angle. So we can say gamma is equal to R plus beta. So R is gamma minus beta. So here we have obtained two relations, I and R in terms of alpha, beta and gamma. In terms of alpha, beta and gamma, the three angles. This is the first step, step 1. This is, I would write as step 1. Find I and R in terms of alpha, beta and gamma. Then I come to step 2. In step 2, we apply Snell's law. So let's take step 2. And in step 2, we apply Snell's law of refraction. This is step 2. So let's apply Snell's law of refraction. We can say 1 mu 2, it is going from medium 1 of refractive index mu 1 to medium 2 of refractive index mu 2 is equal to sin I by sin R. And we can also call it mu 2 by mu 1 is equal to sin I by sin r, and for small angle, sin I is taken as I and r sin r is taken as r. So I'm having another relation here, mu2 into r is equal to mu1 into I. So that is equation number 3. So I hope you could get this. Step 1 was get I and R in terms of alpha, beta and gamma. Step 2 is apply Snell's law and get relation mu to R is equal to mu1 into I. And now obviously we have I and R in terms of alpha, beta and gamma. So I write step 3 here, step 3 here. In step 3, we use equation first and second in third. What we will get? Mu2 into R. R is what? Gamma minus beta. Mu1 into I. I is what? Alpha plus gamma. So I have reached till here and now I can go a little ahead from here. So I have this relation mu2 into gamma minus beta is equal to mu1 into alpha plus gamma. I am writing it here, mu2 into gamma minus beta is equal to mu1 into alpha plus gamma. And then we draw a perpendicular. To further do it, we draw a perpendicular from here. Let's call it A, let's call it B. And you know, due to such curvature, this PB is always negligible. So if we are measuring any distance from B to C, B to I, B to A or B to O, I can always measure, I can always call them from O, from P, from pole, which is always convenient. And for small angle, alpha can be called as tangent alpha, beta can be called as tangent beta, and gamma can be called as tangent gamma. So I put this value mu2 into tangent gamma minus tangent beta is equal to mu1 into tangent alpha plus tangent gamma. And let's put the value of these. So we get mu1, mu2 into what? Tangent gamma. Tangent gamma will be what? AB by PC. Can I write AB by PC? Although it should be AB by BC, but I am preferring it to call AB by PC. Tangent beta will be what? AB. Tangent beta will be AB by BI, or it is AB by PI is equal to mu1 into tangent alpha will be what? AB by BO. This is O. We can also call it AB by PO. So AB by PO. And tangent gamma is again AB by, instead of BC we call it PC. AB gets cancelled everywhere. So you are left with mu2 into 1 by PC. So if I ask you, can you tell me how much is this P to C? So P to C is what? R plus R. All distances are measured from pole. If you are going in the direction of incident ray, then positive. If you are going opposite to incident ray, then negative. Similarly, Pi. So if you are looking for P to I, so this P to I will be what? Plus V or minus V? Your answer should be, it is plus V. So it is V, mu1. And then PO. P to O will be what? PO will be what? Minus U. And P to C will be what? R. So when you are combining all these, I'm just making some space over here. So when you combine all this, you are finally on the conclusion from here mu 2 by R minus mu 2 by V is equal to mu 1 by minus U plus mu 1 by R. So can we call it minus mu 1 over U plus mu 2 by V is equal to mu 2 minus mu 1 by R, and it is the case of rare to denser. So if I just first further clear the situation, you have seen the steps. The steps you can recall how I have gone with. It is not very difficult thing to remember. The first is get the relation of I and R in terms of alpha, beta and gamma. This is step 1. Second step, apply Snell's law. So you get a relation of mu1 I and mu2 R. And then put that value of I and R in terms of alpha, beta, gamma, and then do that assumption for small angle. Alpha is tangent alpha, beta is tangent beta, gamma is tangent gamma. And also neglect this distance. Due to the curvature, we can always neglect and we measure all distances from pole instead of from B. And that's how we have this relation minus mu 1 over U, because it was traveling from a rare medium, plus mu 2 by V is equal to mu 2 minus mu 1 by R, where R is the radius of curvature, U is the distance of object, V is the distance of image, and it was a case of rare to denser. And remember, I told you, for all cases of rare to denser, the formula will remain same. I want to prove it. I want to show it. For all cases of rare to denser, the formula is same. So I'll take now a second situation for you.